Okay, let's go for a brief summary of all of these properties of the renewal chain that we found. Um, so we studied conditions on the parameters Q under which the chain had all these different properties. And let's start with reversibility. So we found that the renewal chain was reversible even only if Qx was equal to 0 for all states 2 and beyond. And why did this make sense? The story was that in general it's very easy to tell which way time is moving when you're being played a movie of the renewal chain. When it's counting downward, you know that the movie is being played forward, whereas if the movie is being played backwards, you would see that the renewal chain being acting as its time reverse chain would actually count upwards. It would go 1, 2, 3 all the way and then jump back to 0, whereas the renewal chain jumps from 0 to some state and then counts back downward. So because of that, most instances of the renewal chain are just not reversible, except for the case where you reduce it to just 2 states. And I use the word reduce in the sense of irreducibility, which we're about to talk about, but we there ensure that the only 2 states that can quote unquote communicate were the states 0 and 1. And when you count with if the only numbers that you know are just 0 and 1 and you're counting, there's no way to tell whether you're counting upwards or downwards. And that led to this reversible feature of the chain, reversible appearance of it. So irreducibility, just mentioned, that had to do with this success probability, the probability of exceeding or equaling state X on an attempt, right? You start at state 0, and the probability Q capital X, you reach X or beyond. And this was needed to make sure that you can go from any one state to the other in a finite amount of time. The K-step transition probability had to be greater than 0 between any 2, and that required us to have this success probability be greater than 0 for every single state in order to reach any state from the other. This had to be true. 0 ended up being kind of the central state that a lot of the analysis centered on. You can consider, for example, the K-step transition probability from state X to Y. Well, if X is less than Y, then you have to first come back to 0 and then try to reach Y. And so in the end, the state 0 played a very prominent role in this example. We didn't talk about transients much, and the reason is that this chain is never transient. So why is that? And this can be a little bit confusing. Let me bring up the definition again. So first of all, a state is transient when rho x is less than 1. So a state is transient when the probability that it returns in finite time is less than 1, meaning that there's some probability that we do not return in finite time. However, we don't get to call a chain transient just because it has a transient state. We can call a chain transient only if all its states are transient. And so that's why I wrote here, there are transient states, but I cannot get all these states to be transient, and therefore I cannot call the entire chain transient. So why can I get all these states to be transient? Well, you can get a lot of them to be transient. Let's go back to the reversible example. Here, states x, x2, x equals 2, x equals 3, and so on. All of these were transient. Once you leave them, you never come back. The transition from 0 to those states is 0, and so you just never return. I could even do one better. I could set qx equals 0 for all x greater or equal to 1, creating just one last state, the state 0, which we just cannot turn into a transient state. So from states x1, x2, x3 in that setup are all transient. You never return to them. You just always reach 0 and stay at 0. But because you stay at 0, state 0 cannot be called transient, and therefore you cannot say the chain is transient. So next I want to make a little bit of a comment about how we write out rho x. So again, rho x was this probability of finite return time. So again, important to recognize that this is a hitting time, the first time that a state reaches state x. Once you imply an initial condition, little x here, then tx becomes, gains this interpretation as a return time, and it may be useful for you to kind of write out this formula. That's a useful one to know about. What does it mean for a random variable to be less than infinity? Well, this is, first of all, a discrete random variable, and it can take on the values 1, 2, 3, right, all the natural numbers. And so I can first of all write that set as a union, like so, and then recognizing that these sets are actually disjoint. There's no way to return in n and n plus 1 at the same time. They're all completely mutually exclusive events. That leads to this sum here. And moreover, the expected return time to state x can now be easily evaluated against this probability distribution. So we did sort of similar things with t naught, but later carried out some calculations with tx as well. So I bet you could even try to calculate explicitly what mx, what the return time to state x actually equals to. We placed a bound on it, but perhaps there is a way to actually compute the exact value. So in the case of positive recurrence, we relied on this theorem, which is an important one. It says that once you establish irreducibility, all your states fall into one of three baskets. They're either all positive recurrent, all null recurrent, or all transient. And so what we did here with the positive recurrent states is we said, well, look, first, before getting any discussion of positive recurrence, you have to have recurrence, and that gave us this condition. This condition gave us irreducibility. Irreducibility then gave us the ability to use that theorem to show positive recurrence for only one state, namely 0. And so we required that this sum here converged. And then that led to the natural extension to say that, well, now because this is finite, then all mx are finite. And we saw this being confirmed on an actual calculation of this. When we tried to place a bound in it, we came up with a condition similar, but the sum ran from a different index. But that doesn't change the fact that the convergence is really in the tail of the sum, not in any finite part of its beginning. Now, null recurrence, again, you need to have the recurrence condition first and foremost. That's this one. And then, of course, as soon as you establish null recurrence of any one particular state, namely the divergence of the series, then you include null recurrence for all states. But again, you need to have irreducibility for this. So that was a must. And then finally, we saw various examples with periodicity. This is an easy chain that you can create any amount of periodic behavior with. And so, there you have it. I may, kind of leave you with a few more comments on when irreducibility is lacking. Right? So we saw this theorem, which is a very powerful one. When you have irreducibility, all the states break down into three different categories, and that's a really useful feature to have. But sometimes you may not get irreducibility, and so you can kind of question, what do I do in that case? Well, you're not entirely out of luck there. What you want to do is approach the problem by reducing the state space to a set over which the chain is irreducible, and then you can apply that theorem. So, just as a quick example here, imagine that I set qx is equal to 0, past some n, right? Maybe not 2, but past some n. Well, what does that mean? That means I'm able to claim that the chain is irreducible on the state space 0, 1, 2, 3, all the way up to n, and then I can apply my theorem in that setup. So hopefully that's helpful, and I think that summarizes essentially all the properties we covered.